Hello everyone. In this video, I will show you how to exploit SLMAIL application using buffer overflow. So for this demo, I have installed SLMAIL application on a XP machine, and the final target would be by exploiting this application, we should be able to gain access to this XP machine. Now I have done SSH so that I should not switch Windows again and again. So I have done SSH from XP machine to my Kali machine, and this Kali machine is having IP address as 192.168.1.8, whereas IP address on the XP machine is 192.168.1.12. So we will first fuzz the application, and then once fuzzing has been done, we identified the crash, and then we will build a exploit from the scratch so that we should be able to gain access of this XP machine. Now I have a fuzzing script with me which will connect to this machine on port 110, and then a user test will be sent out, and then in case of password, one string will be sent out, and that string will start from buffer as 100 bytes and it will keep on increasing with the counter 200. So we need to first fuzz the application. Where does it get crashed? So before I run the script, open the Immunity debugger for the debugging of this application. Go to file, attach SLMAIL process with debugger, and let's run the program. Go back to the Kali and then run the script against XP machine, python sl fuzz.py. So application at the backend is running fine as of now. Now this script will start fuzzing the application. So 100 bytes, 300, 700, 900. So we do see at the backend application is still accepting the traffic. But at around 2900 bytes, we saw application got crashed. So we know that password field can accept 2900 characters, for example, and around that this application is getting crashed. So let's close this. Now we know somewhere within 2900 bytes application is crashing. So what we'll try to do is we will use another script which is basically slmail.py, and this script will send 3000 A's as a password field. If you see in the script, we have defined buffer as A, which is multiplied by 3000. Script will connect to 192.168.1.12 on port 110. Username will be a username and the password will be a buffer, and that buffer is 3000. So we need to see if that application gets crashed again and if we are able to control some of the CPU register by the user supplied input. So I'll talk in a minute about the CPU registers, what exactly we need to control. So let me go back, exit the debugger, restart, stop the application, start it again, bind the application with Immunity debugger, and then run the program. Perfect. Now run the script, python slmail.py. So it will send 3000 A's and application should crash again. So it says sending evil buffer done, and application I could see crashed. An interesting part here is I'm able to control EIP register. EIP register is instruction pointer, and the purpose of this register is it points in the CPU what next instruction to be executed. So if we are able to control this EIP register and plus ESP register, which is known as stack pointer, which is located at the top of the stack, we might be able to insert our code, malicious code, and then we should be able to get the reverse shell of the system. So we do see in 1000 A's this EIP has been overwritten. Now we need to identify exactly those 4 bytes which are being overridden by this in, which are being overwritten, which basically does overwrite of this EIP register. So we need to identify exactly those 4 bytes. So we will take a help of script which is there in Metasploit, and that script can generate 3000 unique characters. And then we'll try to identify after exactly how much bytes this EIP register was overwritten. So go to Kali machine, user, share, Metasploit, tools, exploit, and then we have a pattern create script, and length of the pattern should be 3000. So this script will generate unique 3000 characters, and instead of A, now we will send those 3000 unique characters. So now we have those characters. Copy this, and then nano SLMAIL py. So instead of this buffer is equal to A into 3000, now this time I will send my 3000 unique characters. Okay, done. Control Shift, save it, exit. Just verify the script again. It should have buffer is equal to 3000 unique characters. Go to debugger, detach the process, exit this, and then stop SLMail, and then we have to start the SLMail again. It is taking time because during exploit development you have to basically restart the applications again and again, because we are reaching to a stage where application is getting crashed. So click on start again, immunity debugger, attach SLMail. Let's resume the process, minimize this, and then run the script again, python SLMail py. It works, and we could see now on the back end this EIP register has been overwritten by 39939694438. So again, use Metasploit script, tools, exploit. Earlier we were using pattern create, now I'm using pattern offset. So I will query these 4 bytes within those 3000 unique characters. So that is 39, 69, 44, 38. Now it will do a query within those 3000 unique characters. Now it says there is an exact match at offset 2606. So after exactly 2606 bytes, next 4 bytes, that means 7, 8, 9 and 10, that is being used to overwrite EIP register. So let's verify this. Update the script, nano SLMail. Let's delete the buffer and then buffer again. So we are sending, for example, 2606H. Then I want to send a B 4 in number because we want those 4 bytes to be controlled. Then total value is 3000 bytes, so we'll send basically C, and let Python do the mathematics. 3000 minus 2606 minus 4. Okay, and close the bracket. So now we should see 2606 is, and then EIP is being overwritten by 42, 42, 42, 42, which is the hex value of B, and then I should see 3000 minus 2610 basically C's. Now save the script, exit, let me restart the process, exit, yes, stop it, and then start again. Okay, go to debugger, file, attach SLMail, and start the process. Python SLMAIL py. So you can see EIP has been overridden by user supplied input 42, 42, 42, 42. And if you see ESP is filled with again user supplied input, which is 43, 43, 43, 43. Now we can use this space to send our malicious code. So instead of this junk character C, now we will replace in next step the C with my malicious payload. Now how to tell CPU to execute this code? So that is the responsibility of EIP. If somehow we are able to modify EIP with a valid memory address of ESP, we can redirect or we can control the program execution. So for example, first 2606 age will be there in the memory. The next 4 byte will point to a memory location where our malicious code is there, and that is nothing but the ESP. So we need to identify exact memory location of ESP. And there is a very good script we have in the immunity debugger, and that script is known as Mona script. So with the help of that script, we will be able to identify the memory address of ESP. So let me click on exit, stop this, start it again, and bind immunity debugger with process, attach. Now Mona modules. So we do see there is a DLL called SLMFC.dll, and this DLL being loaded when you run this SLMAIL as an application. Now this is an XP machine. We do not have ASLR dep enabled by default, so every time this DLL will be loaded, the memory location will be the same. So let me try to load the DLL. We should see slmfc.dll somewhere in this list. Let me find it here if we have. So we have loaded the slmfc DLL. Now try to identify if we have jump ESP instruction. So jump ESP instruction will always modify the program execution to the ESP. So let me try to search jump ESP. I could see, but that is something different. DLL NT DLL. Let me again load. Yes, so this is SLMFC. Now SLMFC has been loaded. So right click, go to command section, and then search for jump ESP. So I don't see a jump ESP here. So there is another way. So in some DLLs you will be able to find jump ESP by this process. But if you are not able to identify jump ESP by this process, you need to identify opcode of jump ESP first, and then with the help of opcode we can search the memory location. Now you go to again the Kali machine, and we will take help of amazing script which has been created in Metasploit framework, tools, exploit, and then that is known as Nation. So we'll try to get the opcode for jump ESP instruction. So jump ESP, and now we see the opcode for jump ESP is FFE4. Okay, back to Unity debugger, click on Mona find -s, but we need to find FFE4, quotes closed, -m, and module is SLMFC. So we do see one DLL, one memory location in SLMFC that has got everything is false, safe SEH is not there, ASLR is disabled. So we can use this memory address 5F. Let me note down on a notepad this memory address, and that is 5F 4A 35 8F. Good. So we have one memory location. So let me try to search this. Copy. Uh, Go back to the program execution. Now I want to load this DLL. Search this memory address, and this memory address has got jump ESP. So now try to again focus what exactly we are trying to do. So first 2606 bytes will be in the memory. The next 4 byte will not be having jump characters. Next 4 byte will be this memory location where we have jump ESP as instruction. This instruction will always pass on the program execution to ESP register, and on the ESP we will have one malicious code. So we are almost set how to redirect our program execution with the help of EIP and with jump ESP. Now one interesting step is we need to identify bad characters in our application, which sometimes is a lengthy process. So we need to send all the characters, ASCII characters, and then we need to see which character is not being acceptable by this application, so that while generating payload we should exclude those characters. So let's modify the script a bit. Nano SLMAIL py. Let me. Okay, so we have a buffer, and then let's say I do specify bad characters. Bad char. So we have a bad char from 01 to FF, and then instead of C we will be sending out, because that's a place where we need to put our shell code, bad char. Okay, Control Shift O, Control Shift X, and we have application in running state. Then launch the script. It's run. Interesting stuff. Go to ESP in dump, and we do see 1 2 3 4 5 6 7 8 9, and we see after 9, logically it should be after 9 it should be 0A, and I don't see 0A. It is some random character which is 29. Okay, let me exclude this. So we need to exclude that 0A from the payload. Go to Kali again, then nano SLMAIL py, and then we need to exclude 0A. So you need to repeat this step again and again till the time you didn't get the final number of bad characters which are not being accepted by this application. So I'll not repeat this step again and again. I know what all characters are being not accepted here. So 00, 0A and 0D is another one which this application does not accept. You guys need to try by your own when you will be doing this fuzzing. So I have removed 0D as well from the script, and then I don't need bad characters anymore. Remove this, and instead of bad character now I need to define a shell. Okay, let me take another session of Kali, and use msf vino to generate a shell. Windows shell, I don't need meterpreter, so you can try with meterpreter as well. Shell reverse TCP, so connection will be made with my Kali machine 1.8 on port 443 for example. Bad characters to exclude x00, x0a, x0d, and then format is for example C. So by default the payload will be encoded using Shikata, so we should be able to see that in output. Okay, copy this, go to script again copy the payload here in the script, close the bracket, and what else? So we have shell, we know how it will be, how basically the instructions will be executed. We have the memory address, so that's a memory address. So we need to specify the memory address in reverse fashion. That's how the architecture has been created, basically microprocessor architecture. So we need to specify 8F35 x 8F x35, then x 4A 5F 4A 5F. So we have 2606H, and then EIP will be overwritten by this memory location which is of jump PHP, and then jump PHP should have my payload which will be executed. So this payload is encoded using Shikata. So first payload will be decoded, and for that decoding we need to basically specify few knobs. The purpose of that knob is the moment no operations, the moment CPU will see that specific instruction, CPU will not take any actions, and we need some space to decode my shell. So I will send around 10 knobs, and then it will be a shell. So 2606, we have a memory location, then we have knobs 10, and then shell. So let's try. So Control Shift O, Control Shift X, script has saved. So netcat to listen to the connection if we are able to successfully exploit this application. Close the debugger, then let me restart the application. Stop, start it again. So application is running. Let's verify the IP address 1.12. We have a listener set up, and then run Python SLMAIL py. Script has been executed. Let's see if we have a shell. Yes, we have a shell. IP config. So I can see we are actually on 192.168.1.12 IP address. So that is very basic example of buffer overflow, vanilla buffer overflow, wherein we are able to control EIP. There are no security protection mechanism at the application level or at the operating system level, and we are able to exploit the vulnerability in the password field of SLMAIL. So that's it for this video. Thank you very much. I'll come up with another video with the same concept. Thank you.